Welcome to The Explainer. If you are a diploma computer engineering student gearing up for Digital Electronics Fundamentals, or DEF for short, you are in the exact right spot. We're going to peel back those layers of software and look at how these machines actually think at the bare metal hardware level.
Take a look at this quote. It totally nails our goal here. I mean, at first glance, a smartphone feels like pure magic, right? But as future computer engineers, we don't rely on magic. Our entire job is to turn that illusion into logical, concrete, and replicable engineering.
Here's our roadmap for today. We'll cover the magic of digital logic, how to speak the computer's native language, the 5 core units of your syllabus, building actual hardware projects, and finally your blueprint for success.
Okay, kicking things off with Section 1, the magic of digital logic.
Think about this for a second. Every single time you unlock your phone with your fingerprint, snap a photo, or just play a track, you're relying heavily on basic digital logic. DFI is literally the bridge that connects a high-level software command to a physical hardware response.
And it all boils down to a very strict 4-step flow. It takes an input, like your fingerprint. It pushes that data through a logic layer, which is basically making a brutal 0 or 1 decision. It checks that against its memory and, bam! It produces an output, like unlocking your screen. Everything we're going to build in this course fits right into this exact loop.
Moving right along to Section 2, speaking the computer's language. So why do computers need digital states anyway? Well, picture an old-school analog volume knob. It's a smooth, continuous ramp, right? But computers, they can't do maybe or sort of. They absolutely need clear, reliable thresholds to make split-second decisions. Like, if you raise your hand halfway, is it up or down? A computer needs a hard threshold to definitively say, yep, that is a 1, or nope, that is a 0.
Let's actually try this out right now. We know machines use zeros and ones. Using the 8421 method, the decimal number 13 is encoded as 1101 in binary. Why? Because 8 plus 4 plus 0 plus 1 equals 13. So think about the last digit of your own student roll number. How would you encode it using just those 8, 4, 2, and 1 building blocks? Figuring that out is basically your very first win in speaking computer.
All right, Section 3, the 5 core units.
This syllabus is your roadmap from software user to hardware builder. Unit 1 is kind of like a power of 2 cashier. You're going to learn exactly how machines represent everyday decimal data. We'll be converting our human numbers into binary, octal, and hexadecimal formats. It's really just about figuring out which specific notes the cashier needs to pay the exact amount using only powers of 2.
Then, in Unit 2, we get into how computers actually make decisions using Boolean logic and basic gates. Notice how an AND gate truth table outputs a 1 only when both input A and input B are 1s. It's exactly like a UPI payment. It only goes through if the PIN is correct and your balance is sufficient. Both conditions absolutely have to be true.
Unit 3 is where things get super cool because we start optimizing hardware. We use this tool called a Karnaugh map, or K-map. I love to call this the Google Maps for logic. You arrive at the exact same destination, but you find a way shorter route, which means your final circuit is going to use fewer gates, draw less power, and operate with way less delay. It's just pure engineering efficiency. Next up, Unit 4. This one covers arithmetic calculation and routing data. Whenever we talk about multiplexers and demultiplexers, just picture a railway system. A multiplexer, or MUX, is like a station taking passengers from a bunch of different lines and routing them onto one main outgoing track. A demux does the exact reverse, and that is precisely how your CPU selects and routes data around so efficiently.
Wrapping up the core units, Unit 5 brings in state and memory. We're contrasting combinational circuits with sequential ones. A combinational circuit is like a kitchen mixer grinder. The output only depends on what you're putting in right this second. It has 0 memory of the past. But a sequential circuit, that's like a cricket scoreboard. The output on the board depends on what's happening on the pitch right now, plus the historical state of the score from the previous overs. We build that hardware memory using tiny components called flip-flops.
On to Section 4, building useful hardware projects. Okay, understanding the math is great, but as engineering students, we need to know how to actually build stuff in the lab. Our methodology here is highly interactive, no blindly following instructions. First, you predict an outcome. Then you discuss it with your lab partner. Next, you actually build the physical circuit. After that, you have to explain why it works. And finally, you reflect on the debugging. Because trust me, things will go wrong, and that's exactly where the real learning happens.
And you won't be building random, useless circuits either. You'll actually choose from a menu of micro-projects. You could build a smart room light using NOT gates and sensors. Or maybe a quiz lock system for a game show. You could design a 4-way data selector or build a working score counter. The whole point is to apply this fundamental knowledge to real-world hardware that you can actually touch, test, and be super proud of.
Finally, Section 5, your blueprint for success.
So with all this exciting content ahead, how do you logically conquer this 150-mark subject? Well, first, look at how you're being evaluated. 30% of the exam is just remembering the definitions and rules. 40% tests your deep understanding. But a massive 30% is completely dedicated to your ability to apply these concepts to brand new problems. Rote memorization is really only going to get you about a third of the way there.
To really ace this, I highly recommend using the 3-round method. Round 1, understand the concepts by reading the material and checking past questions. Round 2, try solving the problems completely blindly without peeking at the answers. Round 3, aggressively check your work and rewrite the steps you missed. And seriously, always make sure your circuit answers include a definition, a diagram, a truth table, the Boolean expression, and a working explanation.
Also, keep our lab contract in mind. To make the most of our time, come prepared with a quick 5-minute preview of the material. When you build, think out loud so your partner follows your logic. Build safely. Please, always power off before rewiring. Share your tools, help your team out, and most importantly, embrace debugging. Mistakes in the lab aren't failures. They're literally just data pointing you to the correct fix.
I love this Anton Chekhov quote because it's so true for us. Understanding the theory of digital electronics only matters if you actually get your hands dirty. The magic officially vanishes and the real engineering begins the exact second you pop that first integrated circuit onto your breadboard and wire up the power.
Before we wrap up this explainer, I want you to do a quick mental exit ticket. Seriously, take a second and think about this right now. Name one digital device you use today. Now figure out exactly what its inputs and outputs are. Finally, ask yourself, how does knowing the fundamental hardware logic behind this device apply to the future computer engineering projects you want to build?
You've now got the roadmap to understand how a high-level software command becomes a physical, measurable hardware reality. You're about to learn the actual language of the machine. So the only question left for you is this. Now that you know the language of hardware, what digital magic are you going to build next?